So what do you think still? I mean, just do you feel this is optimal? More or less? What about the dependence on epsilon? Do you think you can get maybe square root of log 1 over epsilon in seed length? Maybe log? Sorry? Right, so you can never go below log 1 over epsilon in seed length. Because if the seed length is less than log 1 over epsilon, it means that you have less than 1 over, depending on the constant, but it means that you have less than 1 over epsilon elements in the set. And therefore, you can guess the element that was sampled with probability at least epsilon. Right? If I have like 4 elements with probability 1/4, I'll guess the element. Like very naively, I'm just going to guess it's 0, 0. Like that's the seed. And then once I know the seed, I know the behavior of the PRG. So you can never go below log 1 over epsilon in seed length. The other parameters, well, this is like problem dependent. And it would have been great if there was some way for us to be able to know, like going back to here, it would be a nice way kind of to ignore explicitness. I mean, the small bias sets are explicit, more or less. I'll talk about it afterwards in a second. But ignoring explicitness, it would have been great if we had a way to figure out what's the shortest seed possible, or at least a good bound, right? For the PRG, right? Would you agree that that would be a very nice thing to have, like a way of telling us what's the best, or maybe what's probably the best seed length for a PRG, even without knowing the PRG? Do you think there is a way of doing that?
Yes.
Yes.
Probabilistic method.
Exactly, the probabilistic method. That's a bit kind of weird, because what I'm going to do now is to show using the probabilistic method, like a two lines proof, right? That good PRGs exist. And the weird thing about it is that PRGs are random, like these are random functions, right? They get a random seed and output things. So there is something like just psychological, not anything like mathematical, something weird about sampling random functions, right? Because you sample the function and then that function sample a seed. So I don't know, it always a bit confuses me. So the little theorem that we are going to prove now is that any class of functions, and again, I'm sticking with Boolean functions, but you can generalize everything, has an epsilon PRG. I don't know whether it's not going to be explicit the way I'm defining it, of course, but with seed length, which is kind of remarkable. So it's 1. I know that when you multiply a number by 1, it doesn't change, but it's 1 times log, yeah? So the base 2 here and the base 2 here. The size of C plus 2 log 1 over epsilon plus a constant, which I never remember. That's a remarkable theorem. It tells us that you don't have to, there does not have to be some structure to the set C, like linear tests or, what have you, in order to fool it. Every class can be fooled. And fooled to with very strong parameters. This is going to be great. The only problem is that probably, most likely, and actually essentially probably, most of these PRGs, like for most classes, most of the PRGs are going to be inefficient. Okay, in whatever way you want it to be efficient. So there are PRGs which are great. It's just that it's not clear how to find them, and if at all, explicit versions of them exist, or efficient, depending on related to the discussion with the time. So, for example, in our case, even before the example, just to be on the safe side, how many functions do you have here?
2 to the 2 to the n.
Right, 2 to the 2 to the n. So that means that theorem is not weird. I mean, this log becomes an n. right? 2 to the n, that becomes an n. And yeah, clearly every function has a PRG with seed length n. You just use the uniform n-bit string, right? That's your PRG. So this theorem becomes, so it calibrates correctly. The two logs here corresponds to the fact that they are like 2 to the 2n function. So it's not weird. But in our case, for example, for decision trees, how many depth m decision trees do we have, right? How many depth, sorry, size. How many size m decision trees on n bits, right? On n inputs do we have, right? So if you have like m leaves, it means that the number of vertices altogether is like maybe 2m or something, right? At most 2m vertices. And for every vertex, what do you have to decide in order to specify the tree structure? I mean, I'm counting how many decision trees do we have. So on n input variables. So I'm saying, if you have size m, you don't have too many vertices, like order of m. And for every vertex, two different decision trees will differ by saying what's the variable there, right? So you have n options at every vertex to put there, and the 0 and 1 doesn't really matter. You can just flip it. Like you can always go left and right, 0 and right, 0 left, 1 right. So what I'm saying is that the number of decision trees is something like, so you have n options, order of n times. Right, you have n options here, n options
Wait,
here.
but what about the architecture of the tree?
Right, so I can kind of assume it's complete, and that's kind of essentially the worst case because you just reject things. Like if you decided not to go somewhere, if you decided on the input here, for example, you can just expand it like in an artificial way. Just read some variable, completely ignore it, and keep outputting the same value.
But is it in the worst way against us and not for us? Because in the sense, when you assume that, you say that m is after you added a lot. So the actual
Okay. I see
is
what you're
much
saying.
smaller.
No, you're right. So maybe I need to slightly improve my count on the number of trees. But it's still going to be linear in M. I need to think about it, but you're right. I shouldn't just add more to the size and not note that I increased the size, right?
Yeah, I didn't think it through to see if it's for us or against us, but I'm not sure.
Yeah. Okay. But okay, I'll check that. But essentially, that's the number of decision trees that you have, size M. It's just that my explanation is not correct. And maybe there is an M square. I don't know, but that doesn't matter. Let me just be on the safe side. I mean, what you're saying will relate to M, not N, right? Just this three structure.
Yes, M.
Right. Good. So this is definitely going to be probably M. It's going to be the bound on the size of the family. And if you take 2 log of that, right, to plug it here, so you'll get something like, the first log will give you something like poly M times log N, right? So this is C. So log C is this thing. And the second log will give you like a log N, kind of surprising, plus log M, up to orders, up to all. That's why I don't care about the poly. So the probabilistic method actually tells you that there is a PRG for size M decision trees on n variables whose seed length in M and epsilon is as we got. It's logarithmic, but the dependence on n is actually double logarithmic. Okay? I don't know if I think it's somewhat surprising. Okay, so that's what it is, and we know how to construct it also, by the way. But without this probabilistic method, I mean, we would kind of get stuck. Can we do better? Can't we do better? With the probabilistic method, you can actually prove that immediately.
We also had multiplicative log 1 over epsilon before, and now it's additive.
No, it was additive. See, it's log n plus log n plus log 1 over epsilon.
Oh, yes.
In a second, we'll have a multiplicative one, so that's why I know that. Which is weird. Why do we have a multiplicative one if we already have an additive one? But We'll see. Okay, so maybe I'll just leave the theorem proof to you. It's very easy. The thing you do is just sample a PRG at random. That's it. And use Chernoff to say, well, I'm facing against, maybe I'll just do the sketch. I'm going to union bound, so that's a proof sketch. It's exactly what we did for linear tests last lecture, last week, but I'm just not only considering linear tests, right? So if you remember last time we said we fix a linear test, we had n linear tests, now we are going to have C functions, and then we just use Chernoff, like completely use Chernoff, ignore the structure of the function and everything. So that's what you do here. You're going to say, I'm going to apply Chernoff. If the seed length is R, then the number of the set size of the output of the PRG is of size 2 to the R. So I'm doing 2 to the R experiments, right? And Chernoff tells me that the probability that I will deviate from the actual expectation, which was 0 for linear test, but it's a general statement, Chernoff bound. So the probability that I will deviate by epsilon after doing 2 to the R experiments, corresponding to the 2 to the R possible values for the seed, is this thing. And when you union bound, you get this expression. And what do you want to do with this expression? This is union bounding over all f in C. And this is the probability that the PRG, when you sample the PRG, right? It's kind of crazy, fails for f. So, the probabilistic method, what do you want to?
I want it to be smaller than 1.
Right, exactly. I want this to be smaller than 1 because once it's smaller than 1, I know that there is a PRG that fools all tests, all functions in C. And now if you just, take this to the other side and log twice because you have E and 2 to the R, you get that R is at least log C plus 2 log 1 over epsilon suffices, plus a constant because this E is something and there is a constant here which I'm lying about. But it's just an additive constant because you log twice. Okay? So these two is like inherent, it's kind of standard deviation coming from these two. And that one is coming, well, I don't know, from the fact that this is a C and not something larger than that. Good. So that's the main tool for us to kind of pinpoint where we are shooting for, right? Like when you construct PRGs. Okay. Any questions? Kind of ignoring the fact C is going to grow when we fix the origin input. No, so C is not growing. C is like the class function size. It will increase with n if you are considering like decision trees with more variables and stuff like that. But then it will reflect in the seed length, which also will increase with n, if that's what you mean. I hope I understood the question. I'm not sure. Right, so again, it's kind of weird that, for me, it's weird that the probabilistic method gives you a way to prove that randomized algorithm exists, right? But they are not really algorithms, right? Because when you say algorithm, the context you have in mind is efficiency. And here, I don't talk about efficiency. I'm just saying that there is a function. There is a function. There exists a PRG for the class. Yeah. Okay.
If I want to consider different distributions than the uniform, is it just the same because I can think of a uniform and then a function that deforms it into a different one? So I take n that is slightly larger and deform it or something like that?
Right, yeah, so good. So actually, that relates to, there are two uniform strings, the R-bit string and the N-bit string. You're referring to the N-bit string, right?
Right.
Right. So, good. So we only talked about uniform N-bit strings because that's like the typical off-the-shelf things people want. But yeah, right. If some algorithm for some reason or for some other reason, not only algorithms, they want some other distribution, then you can define this notion of a PRG for that distribution, so it outputs that kind of distribution. But right, usually it's just another layer. So you do the PRG, you get uniform, and then there is the question of how to sample from that distribution using uniform bits. So it's a kind of, in a sense, orthogonal question that you can ask.